Okay, let's get into this. Today, we're doing a deep dive into a source that's, oh, it's right at this amazing intersection, mathematics and physics.
Yeah, it's fascinating stuff.
We're looking at how these really abstract mathematical ideas, things that seem totally separate from, the everyday world,
Uh-huh.
somehow they end up being the language we use to describe reality, especially when you look at the really small stuff or the really big picture, the universe itself.
That's exactly right. The material we're drawing from today, it really explores these deep connections, sometimes quite surprising links between math, physics, and, well, some of the biggest mysteries out there.
And our goal here is to walk you through some of the most interesting concepts the source brings up. We'll start with things that might feel familiar, maybe geometry.
Like Pythagoras, yeah.
So exactly. And then we'll travel into some really strange territory, like quantum mechanics and the puzzles around gravity and the cosmos. We want to pull out the surprises, the key ideas, and help you see why this link between abstract math and physical reality is just so crucial.
Think of it like we're trying to understand the rule book the universe uses and, why that rule book seems to be written in math. So yeah, let's jump in.
So where does this relationship, this sometimes unexpected connection, really start to show itself? Our source takes us right back to something we probably all did in school: geometry,
Hmm.
specifically the Pythagorean theorem. You know, a squared plus b squared equals c squared. For right-angled triangles, feels totally solid, right? Like universally true.
It really does. And the Force uses that familiarity, that feeling of certainty, as a launch pad to
Yeah.
show that this geometry we learned first, Euclidean geometry, it's actually not the only kind there is.
Wait, so the Pythagorean theorem isn't always true?
Not in other geometries, no. That theorem, it depends on the space being flat in the Euclidean sense.
That feels wrong somehow. Like the rules for triangles change.
Depending on the geometry of the space you're in, yeah. The source points to things like M.C. Escher's drawings, those patterns. Fish or angels filling the
Oh,
space.
yeah, the tessellations.
Exactly. In some of them, like the fish ones that seem to shrink towards the edge of a circle.
Right, I know the ones.
Well, that shrinking isn't because the fish are actually getting smaller. Escher is mapping a different kind of space, hyperbolic space, onto our flat Euclidean page.
Ah, so he's showing us what that curved space looks like, projected flat.
Precisely. The hyperbolic space itself is uniform, looks the same everywhere if you were inside it.
Yeah.
But its basic structure, its geometry, is different from flat space. And these non-Euclidean geometries, they turn out to be vital for understanding the actual shape of our universe on the largest scales.
So our universe might not be flat in the way we assume.
It could be. It seems pretty close to flat, but it could also be hyperbolic or even elliptic on a grand scale. And suddenly that simple theorem doesn't quite work, but the deeper mathematical ideas about geometry become essential for cosmology.
Okay, geometry is deeper than it looks. What about numbers? We start with counting, then fractions, rational numbers. The source brings up the ancient Greeks, bumping into a problem with just the diagonal of a square.
The square root of 2, yeah. A
Yeah.
symbol length, but it's not a rational number. You can't write it as a fraction.
Right. And that forced them beyond fractions, eventually leading to the real numbers. We tend to think real numbers perfectly match up with things like length or time, don't we? Continuous things.
We do. We use them as our model. But the source asks a really interesting question here. Is that connection between the mathematical idea of real numbers and physical reality quite as perfect as we think?
How do you mean? We measure lengths all the time.
Sure, we use real numbers for measuring, but can we physically see infinite precision? Can we actually distinguish those infinitely tiny differences that the mathematics of real numbers allows for? Things like Dedekind cuts, these purely abstract ways of defining real numbers.
You're saying we can't actually see that infinite detail in the real world.
The source suggests maybe not. Perhaps the physical world, at its most fundamental level, isn't perfectly continuous in the way the mathematical real numbers are. Maybe the math outstrips the physics slightly.
Huh. So the abstract idea might be richer than reality itself in a way.
It's a thought-provoking point the source raises. And this leads us somewhere even more abstract. Complex numbers, involving I, the square root of -1.
Oh yeah, those definitely feel purely mathematical, imaginary number.
Exactly. They sound theoretical. But here's where the source talks about this incredible mathematical magic.
Because they turn out to be essential for physics.
Absolutely fundamental. According to modern physics, especially quantum mechanics, the rules governing the universe at the smallest scales are deeply, intrinsically tied to complex numbers, even though they seem less intuitive than real numbers for just measuring things.
Uh-huh.
They are completely necessary for describing quantum states and how they evolve over time.
Is that where Euler's formula comes in? E to the pi times I plus 1 equals 0. That always seemed weirdly profound.
Yes, the source calls that almost mystical. It links 5 of the most fundamental constants in mathematics, 0, 1, I, pi, and e in one elegant equation. It's like a huge hint that these numbers are woven together in a really deep way.
And they connect to geometry too, right? Multiplying by I.
It's a rotation. Multiplying by I in the complex plane is like rotating something by 90 degrees. It ties the arithmetic of numbers directly to the geometry of rotations. Beautiful.
Right, like turning the number 1 into I on that vertical axis.
And complex numbers also lead to even fancier geometric concepts. You can think about gluing patches of the complex plane together to make surfaces, like a donut shape, a torus.
Okay.
The source mentions this as one of the first examples of what mathematicians call a manifold.
And manifolds are crucial for Einstein's general relativity.
Absolutely central.
Yeah.
A manifold is basically a space that, if you zoom in really close on any point, it looks like ordinary flat Euclidean space,
Yes.
like the surface of the Earth looks flat locally. But globally, it can be curved.
Oh, okay.
And this idea of smoothly curved space, or spacetime, is the mathematical heart of general relativity. Spacetime itself is treated as a curved manifold.
Okay, so abstract geometry, even complex numbers, they're not just curiosities. They're fundamental to describing space-time. Now, let's switch gears a bit to the quantum world and its often tricky relationship with relativity. The source points out a major tension there.
Oh, a huge tension. You see, the standard quantum mechanics, the original version, treats time very differently from space. Time is this special external parameter, teet, that just ticks along, governing how everything changes.
Right.
But space coordinates are treated more like labels for where things are. This clashes badly with special relativity.
Because relativity mixes space and time.
Exactly. Special relativity says space and time are woven together into space-time. There's no universal preferred time ticking the same for everyone. So the way standard quantum mechanics describe change over time just wasn't compatible with the symmetries that relativity demands.
So how did they try and fix that? What was the solution?
Well, the source highlights Dirac's brilliant insight. He wanted a quantum equation that was compatible with relativity, but also simpler in how it handled time derivatives, more like the original Schrödinger equation.
Oh, okay.
And his solution involved, mathematically speaking, taking a kind of square root of a key operator, the wave operator, in a really clever, relativity-friendly way.
Taking a square root of an operator.
Wow. Okay, the math is getting abstract again.
It definitely is abstract math. But doing this forced him to introduce extra mathematical bits and pieces into the description of the particle. And operators for these new pieces had a strange property. They didn't commute.
Meaning the order you applied them mattered, like A times B isn't B times A.
Precisely, unlike normal multiplication. And here's the astonishing part. These extra non-commuting mathematical objects, which are purely required to make quantum theory work with relativity,
Yeah.
they turned out to perfectly describe something physical, the intrinsic spin of particles like the electron. Spin wasn't just added in, it popped out of the mathematics needed to combine quantum mechanics and relativity. Whoa. So spin was basically predicted by the math reconciling those two theories. That's amazing. And didn't the Dirac equation predict something else really big?
It did. Antiparticles. For every particle, like the electron, the equation predicted a corresponding antiparticle, the positron in this case.
Yeah.
Same mass, but opposite charge in other quantum numbers.
Antimatter.
Antimatter, yeah. And the source explains how this leads to particle-antiparticle creation and annihilation. You need enough energy, at least twice the particle's rest mass energy, to create a pair out of nothing. And they can wipe each other out, turning back into energy.
And if particles can be created and destroyed, you can't just think about a fixed number of them anymore.
Exactly. That realization, driven by Dirac's equation, basically forced Phelps to move beyond thinking about single particles to developing quantum field theory, or QFT.
Where particles are more like ripples in a field.
That's the picture.
Yeah.
Excitations in underlying quantum fields. QFT is the framework we use now.
And QFT brought us things like Feynman diagrams, right? The source mentions that zigzag picture for an electron.
Feynman diagrams are fantastic tools. They let you visualize particle interactions. That zigzag, depending on how you look at it in space-time, can represent an electron moving forward in time, then backward, then forward again.
Backward in time.
It's a way of thinking about antiparticles, actually. Or you can see it as interactions happening through the exchange of virtual particles. They pop into existence just long enough to mediate a force, then disappear.
Like static electricity, two electrons pushing each other apart.
In QFT, that repulsion-Mahler scattering technically isn't just two things pushing. It's pictured as one electron spitting out a virtual photon, like a little packet of the electromagnetic force, and the other electron catching it.
So the force is carried by these virtual particles.
That's the idea. The familiar electric force emerges from this constant quantum exchange.
Okay, QHT sounds powerful, but even within quantum mechanics, there's still this really deep puzzle the source talks about, the measurement paradox.
Ah, yes. This is maybe the deepest mystery of all. Quantum theory seems to have two completely different ways things can change. First, there's the smooth, predictable evolution described by the Schrödinger equation. We call it U-evolution. It's deterministic.
Okay, smooth change. What's the other way?
The R process, reduction, or collapse of the wave function. This supposedly happens when you make a measurement. Instead of smooth change, the system state suddenly jumps, randomly and instantly, to one of the possible outcomes you could measure.
And the problem is these two processes seem totally different, right? The source uses the beam splitter example.
Exactly. Imagine sending a single particle, like a photon, towards a half-silvered mirror, a beam splitter. According to the smooth U-evolution, the particle's quantum state splits. It describes the particle simultaneously taking both possible paths after the mirror.
So it's in a superposition of being on path A and path B.
Right. You could send those paths miles apart to two different detectors. The U-evolution says the quantum state is spread out, representing both possibilities. But when a measurement happens, only one detector clicks. Ping. Instantly, the state seems to collapse, so the particle is found entirely at one location, not the other.
It's like the quantum fuzziness disappears the moment you look. It picks a side.
That's what it looks like. And the source brings up Schrödinger's famous cat thought experiment to show how bizarre this gets if you try to apply only the smooth U-evolution to macroscopic things.
The cat that's linked to a quantum event, so it ends up alive and dead at the same time.
In a superposition, yeah.
Yeah.
Which is absurd in our everyday experience. We never see cats like that.
So what do physicists make of this? The source says most try to interpret it within the current theory.
That's largely true. Many interpretations try to explain how this apparent collapse happens, or argue it's not really a physical process. Maybe it's about information or interactions with the environment causing decoherence. But the source author and others take a different view. It's that this fundamental clash between the smooth U process and the jerky R process means quantum mechanics as we know it is actually incomplete.
Right.
That we need a new, deeper theory that explains why measurements give definite outcomes.
And concepts like superposition and entanglement are all tangled up in this weirdness.
Definitely. Superposition is just being in multiple states at once, like the particle taking both paths.
Yeah.
Entanglement is even weirder, the EPR paradox idea. Two particles are linked, maybe created together, so measuring something about one, say its spin,
instantly tells you something about the other one, no matter how far apart they are.
Exactly. Their fates are correlated in a way that defies classical intuition. It's like they're still connected.
And things like density matrices help describe these states?
Yes. Density matrices are mathematical tools for describing quantum states, including situations where you might have a mix of possibilities, not just a pure superposition. For simple systems, like the spin of an electron, you can visualize all the possible quantum states using the Bloch sphere. Every point on the surface of this sphere corresponds to a specific direction the spin could be pointing. It's a neat geometric picture of the abstract quantum possibilities.
Huh. A geometric map for quantum states. Okay, let's shift again to the really big scales and deep time mysteries. Gravity, cosmology, and the arrow of time. Why does time only flow one way? The source dives into that too.
It's a huge puzzle. Because the fundamental laws of physics we know, Newton's laws, electromagnetism, relativity, even the basic Schrödinger equation, they mostly don't care about the direction of time. They work just as well forwards as backwards.
Like running a movie in reverse. The physics still makes sense for simple interactions.
Pretty much. Yet in the world we see around us, time clearly has a direction. Broken eggs don't unsbreak, things wear out. That's the second law of thermodynamics.
Entropy always increases. Disorder tends to grow.
Right. And the source explains entropy using Boltzmann's idea. It's related to the number of microscopic ways you can arrange the bits of a system so it still looks the same overall, macroscopically. A messy room can be arranged in many more ways than a tidy one. High entropy means lots of possibilities.
Okay, but how does that connect to the Big Bang? The source called it a conundrum.
Well, if entropy always increases as time goes forward, then if you run the clock backward towards the Big Bang, the universe must have started in a state of incredibly low entropy, extremely ordered.
But wait, didn't the early universe start as a hot, dense soup? The hot Big Bang model says it was in thermal equilibrium, everything mixed up. Isn't that high entropy?
That's the crucial point. For the matter and radiation within it, yes, being uniformly mixed at high temperature is a high entropy state. Maximum randomness for the stuff.
Not for gravity.
Exactly. Gravitationally speaking, a perfectly smooth, uniform distribution of matter is actually a state of extremely low entropy. Gravity wants to clump things together. Clumps are higher gravitational entropy. Smoothness is very special, very ordered gravitationally.
Oh. So the early universe was thermally high entropy, but gravitationally very, very low entropy.
Precisely. The source uses this amazing analogy. It's like the creator had to aim a pin at an absurdly tiny region in the space of all possible starting configurations to get the smooth gravitational state we think the universe began with.
That sounds incredibly fine-tuned, like the universe had to start in this incredibly specific gravitational state for the second law to even get going.
That's the argument the source presents, that this initial very low gravitational entropy is the ultimate reason we experience an arrow of time. Things are still unclumping gravitationally, allowing complexity in order to increase locally, while overall entropy grows.
And there are ideas like the Weyl curvature hypothesis trying to explain why it started so smooth.
Yes, that's a more technical idea suggesting the type of curvature allowed at the Big Bang, singularity was restricted, low Weyl curvature, preventing large gravitational clumping initially, unlike the singularities inside black holes, which are thought to be wild and chaotic. High Weyl curvature. It links the geometry of singularities to the arrow of time.
Okay, connecting cosmology and time. Now, what about gravity and that quantum measurement problem we discussed? Could gravity be the missing piece that explains the R process, the collapse?
This is a really fascinating idea the source explores quite deeply. The suggestion is that maybe gravity itself, or something fundamental about space-time structure, is responsible for causing quantum superpositions to collapse into definite states.
How would that work?
The idea is that perhaps when a system gets massive enough or spread out enough in space-time, the conflict between its quantum superposition and the gravitational field it generates becomes too much. Gravity might inherently resist large-scale superposition, forcing a choice.
So, Schrödinger's cat wouldn't stay in a superposition because a cat is just too big and heavy. Gravity wouldn't allow it.
That's the kind of thinking. It would mean the collapse isn't caused by conscious observers or measuring devices, but by an objective physical process linked to gravity or space-time itself. It sets a scale maybe related to Planck energy or mass, where quantum effects give way to definite classical reality.
So the tension isn't just between the theories of QM and GR, but maybe between the principle of quantum superposition and the way gravity actually behaves for real objects.
That's a good way to put it. The source suggests this points towards needing a unified theory of quantum gravity that doesn't just quantize gravity, but also resolves the measurement problem by including this objective reduction mechanism.
And black holes, where gravity is off the charts.
They must offer clues, right? You'd think so. The source mentions black hole thermodynamics, the discovery that black holes have entropy, and it's proportional to their surface area, the Bekenstein-Hawking entropy. That's a profound link between gravity, area, thermodynamics, entropy, and quantum ideas. Planck's constant is involved.
Seems like all these deep theories are connected around black holes.
They really seem to be. The source also touches on ways energy might be extracted from rotating black holes, involving weird physics near the event horizon, possibly powering things like quasars. It hints at exotic effects, where gravity and energy interact strongly.
Okay, those are deep connections. The source wraps up by mentioning some pretty radical, speculative ideas trying to tie all this together, right? About the very nature of reality.
Yes, these are ideas right at the frontier, trying to unify quantum mechanics and gravity, or solve these fundamental puzzles. One major direction is questioning that smooth, manifold picture of space-time we got from Einstein.
So maybe space-time isn't perfectly smooth and continuous down at the tiniest scales. What would it be instead?
There are various ideas. Quantum foam, where space-time fluctuates wildly at the Planck scale. Or maybe space-time is fundamentally discrete, made of tiny atoms of space and time. Things like causal sets, Snyder-Child lattices, Reg calculus, different mathematical approaches trying to build space-time from discrete blocks rather than a smooth continuum.
A kind of quantum graininess to reality?
That's the concept. a huge departure from the smooth geometric picture of general relativity.
And what about extra dimensions? That always sounds like science fiction.
It does, but it has a long history in physics. Kaluza-Klein theory tried it early on. String theory, more recently, often requires 10 or 11 spacetime dimensions to be mathematically consistent.
String theory needs extra dimensions.
Typically, yes. The idea is that fundamental particles aren't points, but tiny vibrating strings, or higher dimensional objects called branes. And the way they vibrate determines the particle properties. The extra dimensions are needed for the theory's math to work out, often with the goal of unifying all forces, including gravity.
But if there are extra dimensions, why don't we see them? Where are they?
That's the million-dollar question for those theories. The usual answer is they're compactified, curled up incredibly tightly on scales far too small for us to probe directly. But the source raises a subtle challenge. If reality is fundamentally, say, 10-dimensional, why does the physics we do see in our familiar 4 dimensions seem relatively simple? Why isn't it obviously reflecting that higher dimensional complexity? Making these elegant mathematical theories match our observed world is still a major hurdle.
So these cutting-edge ideas are pushing math and physics into strange places, but they bring their own big questions about why the universe looks the way it does to us.
Absolutely. It just shows how much we still don't know when we get down to the fundamental nature of reality.
Wow. Okay, we have journeyed quite a distance here. From the surprising depth in basic geometry and numbers.
The power of complex numbers.
Right. To the weirdness of quantum mechanics, its clash with relativity, the puzzle of why time flows forwards linked to the Big Bang.
Yeah, that low entropy start.
And ending with these, well, frankly, mind-bending ideas about discrete spacetime or extra dimensions.
It really underscores how incredibly effective abstract mathematics has been in describing the physical world, sometimes in ways the mathematicians themselves never anticipated.
Definitely right.
It highlights that where our best current theories, quantum mechanics and general relativity, seem to conflict or leave puzzles unsolved, that's where the deepest mysteries lie.
Mysteries like, well, the gap between abstract math and what we can actually observe, the quantum versus gravity conflict, the origin of time's arrow in that weirdly smooth early universe, and that central quantum puzzle. Why do measurements give definite answers? The R process.
These aren't just philosophical head-scratchers. They feel like genuine clues that our current picture of reality might need a fundamental overhaul.
So here's something for you, the listener, to chew on, based on everything we've touched on from this source. Considering these paradoxes, especially the quantum measurement problem and that strange initial state of the universe, does our current physics framework have to change fundamentally? Is quantum theory incomplete? Is our view of space-time wrong?
Could gravity, as the source speculates, be the actual key to understanding quantum collapse, linking space-time structure itself to observation?
Or are all these clues pointing towards something even more radical, a concept of reality so different from what we've discussed that we're only just starting to get hints of it through the strange effectiveness of mathematics?
It's where physics and math push each other into unknown territory. Definitely keeps things interesting and hopefully keeps you curious about these foundational questions.